Of all the ways the universe could end you, this might be the strangest. Fall toward a black hole and you would not be crushed all at once. You would be stretched, slowly at first, then violently, drawn out into a thin stream of matter. Physicists have a name for it: spaghettification. To understand it, start with something gentle. The ocean tides. Twice a day the seas rise and fall, and the cause is the moon, pulling a little harder on the near side of the Earth than on the far side. That difference in pull is called a tidal force. Here is the key idea. Gravity gets weaker with distance. So any large object feels a stronger pull on the side facing the source than on the side away from it. The object gets stretched between those two pulls. On Earth, that stretch is tiny. Near a black hole, it is monstrous. Imagine falling feet first toward a black hole. Your feet are closer, so they are pulled harder than your head. The difference is small at first, a faint sense of being drawn out. But as you fall, that gap in force grows and grows with terrifying speed. Soon the pull on your feet is not a little stronger, but enormously stronger than on your head. Your body is dragged out lengthwise like warm putty, while at the same time squeezed inward from the sides. You become long and impossibly thin, a human noodle drawn toward the dark. The term sounds almost playful. It was popularized by the physicist Stephen Hawking, who described an astronaut being stretched like spaghetti as they fell. The name stuck precisely because it captures something true. The geometry of a black hole really does turn matter into strands. Every massive body has tidal forces. The Earth has them, the Sun has them. What makes a black hole different is how concentrated it is. All that mass is crushed into a single point, so you can get terrifyingly close to it. And the closer you get, the more savage the stretch. Around every black hole is an invisible boundary called the event horizon. Cross it, and nothing, not even light, can ever climb back out. It is not a wall you hit. It is a line in space, beyond which every path leads only deeper in. There is no turning around. Now a strange twist. Smaller black holes are deadlier to fall into than giant ones. With a small black hole, only a few times the Sun's mass, the tidal force becomes lethal while you are still far outside the horizon. You are torn apart before you even reach the edge. The supermassive black holes at the hearts of galaxies are the opposite. They can be millions or billions times the mass of the Sun. Their gravity is gentler at the horizon, spread over a vast region. You could, in principle, drift across the edge of one of these without feeling a thing. Think about how eerie that is. For a truly enormous black hole, you might cross the event horizon alive and whole, with no alarm, no sensation, no warning. The most important boundary you will ever pass, and you would never feel the moment it happened. It is only a reprieve. Even inside a supermassive black hole, the tidal force keeps climbing as you fall toward the center. The stretching that spared you at the edge is waiting for you deeper in. Spaghettification is not avoided. It is only delayed. At the very center lies what we call the singularity, a place where our equations break down and density may become infinite. Everything that falls in is drawn toward it. Whatever you were, particle by particle, is pulled into a line and delivered into a mystery physics cannot yet describe. Now flip the view. Suppose a friend watches you fall in from a safe distance. They would never see you cross the horizon at all. Because of the way the black hole bends time, you would appear to slow down, redden and freeze, hovering forever at the edge. To your friend, you become a fading afterimage, dimmer and redder with each passing second, never quite vanishing, never quite arriving. From the outside, you take an eternity to fall the last short distance. From the outside, you never truly leave. But for you falling, there is no freezing and no eternity. Time runs normally. You cross the horizon in an instant and keep falling faster and faster. The two stories are both completely true. Near a black hole, even the question of when something happens has no single answer. For a small black hole, the whole ordeal is mercifully brief. From the moment the stretching turns deadly to the final plunge, perhaps a fraction of a second. There would be agony, but it would be over almost before your mind could register that it had begun. This is not just a thought experiment about astronauts. It happens to whole stars. When a star wanders too close to a black hole, the tidal force grips it and tears it apart, pulling it into a long, luminous stream. Astronomers call this a tidal disruption event. When a star is shredded this way, part of its gas spirals inward and heats to enormous temperatures, blazing out a flare of light that can outshine an entire galaxy for weeks. We have caught dozens of these flares, the death cries of stars being spaghettified light years away. In recent years, telescopes have tracked these events from the first flicker to the long fading glow. We have measured the streams of torn star matter, watched them whip around the black hole, and seen them slowly swallowed. Spaghettification, once pure theory, is now something we observe. Each flare carries a fingerprint. By spreading its light into a spectrum, astronomers can read the temperature, the speed, even the chemistry of the dying star. The black hole leaves no body behind, but the light of the kill travels outward for us to study. Could a ship or a person ever survive the approach? Near a small black hole, never. The tidal force is simply too steep. Near a supermassive one, you might cross the horizon intact, but you could never come back to tell anyone. Survival and escape are not the same thing. Everything about spaghettification comes back to one humble fact. Gravity is not the same at your head as at your feet. We never notice it in daily life, where the difference is a vanishing fraction. A black hole simply takes that everyday truth and pushes it to its monstrous extreme. The force that would unmake you shapes the whole universe gently elsewhere. It raises our ocean tides. It cracks the icy crusts of distant moons. It slowly locks worlds to face their planets. Tidal force is everywhere, usually patient and quiet. A black hole only removes the patience. No one ever flew in to check. We know all of this from the mathematics of general relativity, the same equations that predicted black holes themselves. The stretching, the frozen observer, the delay before the end. The equations describe the horror in detail long before we saw a single flare. And the singularity at the center is more than a place. It is a boundary of human knowledge. Our best theories of gravity and of the very small refuse to agree there. Whatever truly happens to the matter that falls in, we do not yet have the language to say. Remember the two views. To the one falling, the end comes in moments. To everyone watching, the fall never finishes. In a real sense, anything that has ever fallen into a black hole is, from our vantage, still falling, frozen and reddened at the edge forever. Black holes are not in a hurry. They drift through the dark for unimaginable spans, occasionally catching a star, drawing it out and feeding. On the longest timescales, they may be the last bright things left, lighting the cosmos with the tides of dying matter. There is something clarifying in all this. The thing that would destroy you is not malice or fire, but geometry, the simple shape of space near enough mass. The universe does not need a monster to unmake you. It only needs gravity and a steep enough slope. So the next time you read about a black hole, remember what falling in would really mean. Not a crushing, but a stretching. Not one death, but two stories that never agree. And a thin, bright thread of what you were, traced across the dark, telling the universe you were here. In the end, spaghettification is the universe at its most honest. It hides nothing. It simply takes the ordinary pull you live inside every day, the one you never feel, and follows it all the way down to where it becomes the strangest fate that physics allows.